Hello everyone, this is Bandgar working as Assistant Professor at Department of PHCT242 College, Nasa. Today we are going to discuss M.Sc second year, paper second, Experimental Technique in Physics, paper second, semester 4. Today we are going to discuss the chapter of Structural Characterization and Thermal Analysis. So starting with first concept, Xray Diffraction. So diffraction is due to essentially to the existence of certain phase relations between two or more waves, and it is advisable at the start to get a clear notion of what is meant by phase relation. Coherent scattering of X-ray by crystalline substance. Diffraction is essentially a scattering phenomenon in which a large number of atoms cooperate since the atoms are arranged periodically. On lattice, the rays scattered by they have definite phase relation between them. These phase relations are such that destructive interference occurs in most directions of scattering, but in few directions constructive interference takes place, and diffracted beams are the two essential are wave motion capable of interference, X-ray, and a set of periodically arranged scattering centers, the atoms of interest. Next concept is the production of X-ray. When electrons strike a target or when a electron rearranges within an atom, then X-ray are produced. X-ray are commonly produced in X-ray tubes by accelerating electron through a potential difference, a voltage drop, and directing them onto a target material, that is the tungsten. An incoming electron may also collide with an atom in the target, kicking out an electron and leaving a vacancy in one of the atoms electron say. Another electron may fill the vacancy and in so doing release an X-ray photon of a specific energy, a characteristics of X. See the diagram how to generate a X-ray or production of X-ray by using a X-ray tubes. So the incoming electron release X-ray as the slow down in target, that is the braking radiation brainstorm. Next one is the cyclotron is a device that accelerates electrons in an evacuated ring, often several tens of meters in diameter, steering them with magnets, manipulate the electron beam in a controlled way with the magnets, can produce intense beam of cyclotron facilities are used for research purposes. Cyclotron radiation is emitted by charged particles traveling on a curved path, as would happen while moving through a magnetic field. Since the source of all electromagnetic radiation is the acceleration of charged, cyclotron radiation is an example electromagnetic radiation produced by centripetal acceleration, as opposed to flame hustling, which is produced by a tangential acceleration. Next one is the production of X-ray by cyclotron. The wavelength of this radiation is a function of the energy of the charged particle and the strength of magnetic bending the charge. The spectrum of the radiation is continuous. It's characterized by its critical wave. Cyclotron radiation is organized. The beam is highly polarized. Most of the waves are oscillating in the same plane and collimated. Most of the waves are in the same direction. X-ray tube produce messy radiation that is completely unpolarized and may be focused only with great difficulty. A cyclotron source is like an X-ray laser, while an X-ray tube is like a X-ray floodlight. Next one is the X-ray wave, an electromagnetic wave with wavelength in range of 0.01 to 10 nanometer, corresponding to frequency in the range of 30 petahertz to and energies in the range of 100 eV to 100 keV. X-ray have shorter wavelength, higher energy than UV waves and generally longer wavelengths, lower energy than gamma. Sometimes X-ray are called Roentgen radiation after William Roentgen, who is usually created as their disc. Because X-ray have very high energy, they are known as ionizing radiation and can harm living tissues. A very high radiation dose over a short amount of time causes radiation sickness, while lower doses can give an increased risk of radiation-induced cancer. X-ray are similar to gamma rays, however, the main difference is the way they are produced. Next one is the types of X-ray. It has the two types. First one is the hard X-ray, second one is the soft X-ray. So X-rays are broken into two categories. First one is hard X-ray with energy above 5 to 10 kV, below 0.2 to 1 nanometer wavelength, and hard X-ray are more useful for radiography because they pass through tissue. Due to their penetrating ability, hard X-ray are widely used to image the inside of objects, example in medical radiography and airport security. As a result, the term X-ray is metaphorically used for to a radiographic image produced using this method in addition to the method itself. Since the wavelength of hard X-ray are similar to the size of atoms, they are also useful for determining crystal structure by X-ray crystallography. By contrast, soft X-ray are easily absorbed in air. The attenuation length of 600 eV equal to 2 nanometer. X-ray in water less than 1 micrometer. Next one is the soft X-ray with energy 100 eV to 5 kilo eV. It is the 10 to 0.1 nanometer wavelength. Lower doses of X-ray radiation can be very effectively used in medical radiography, X-ray spectroscopy. In this case, medical radiography, the benefits of using X-ray for examination far outweighs the risks. In medical diagnosis application, low energy soft X-ray are unwanted since they are totally absorbed by the body, increasing the radiation dose without contributing to the image. Hence, a thin metal sheet, often of aluminum called an X-ray filter, is usually placed over the window of the X-ray tube, absorbing the low energy part in the spectrum. This is called hardening the beam, since it shifts the center of the spectrum towards high energy or harder X-ray. Next one is the continuous and characteristics radiation of X-ray. The material of the target affects the intensity but not the wavelength distribution of continuous radiation. When the voltage on an X-ray tube is raised above a certain critical value, characteristics of the target metal sharp intensity maxima appear at certain wavelength superimposed on the continuous radiation. Since they are so narrow and since there are wavelengths are characteristics of the target metal used, they are called characteristics lag. The continuous spectrum is due to the rapid deceleration of the electron hitting the target since mentioned above. Any deaccelerated charge emits energy, while the continuous radiation is caused by the rapid deceleration of electron by the target. The origin of the characteristics radiation lies in the atoms of the target material. So following spectrum shows the characteristics and continuous radiation of the X-ray. So we have to say the K beta, it is the K alpha, it is the characteristic radiation, and another non-linear curve of the X-ray wavelength is the continuous. Now continuous, or it is also known as the white X-ray radiation. Continuous X-ray are created when free moving electrons electromagnetically interact with nuclei, where characteristics X-ray are for during the electron transition process that occur when an inner shell electron is released from an atom. Weinstrahlung transition tend to create a phenomenon of continuous X-ray, whereas the regular characteristics X-ray are produced by inner shell transition. It is also called as polarimetric, continuous, and or white radiation. The Weinstrahlung breaking radiation mechanism can be viewed when a target made of metal suffers electron bombardment. The atoms of the target metal scattered the electrons whose change in acceleration cause a phenomena of radiation in them. Continuous X-ray radiation is for the fact that the change in the velocity which causes the emission of much of the radiation into which is used as a radiography source is a random process that emits photons at different energy. Characteristics X-ray are discharged from the heavy elements when the electron make transition between the lower atomic energy levels. The generated X-ray wavelengths will be distributed over a range which may or may not include the characteristics ones. Depending upon the energy of the bombarding electron, the generating X-ray wavelengths will be distributed over a range which may or may not include the characteristics ones depending upon the energy of the bombarding electrons. Since the energy level are discrete, short reason, a consequence of quantum mechanics or probability distribution. They are usually X-rayed with a very specific energy that depends on the element. Whenever the tube voltage is very low, below 60 kV, we should be able to see some strong peaks due to the characteristic radiation of emission from the target, that is the anode material. Now, next one is the Bragg's diffraction law. So, diffraction is generally occurs when the wavelength of the wave motion is of the same order or magnitude as the repeat distance between the scattering set. This is requirement follows from the Bragg's. Since sin theta cannot exceed unity, we may write n alpha upon 2 d dash is equal to sin theta less than. So where n alpha less than 2 d dash for diffraction, n is equal to 1. So minimum when we have to perform a diffraction, at least we have to put the n is equal to put the 1 in. The condition for diffraction at observable angle 2 theta is lambda upon 2 d dash. On other hand, x is very small. The diffraction angle are too small to be conveniently measured. The Bragg's law may be written in the form of lambda is equal to 2 d dash upon n sin theta. The coefficient of x is now unity. We can consider a reflection of any order as a first order reflection from planes, real or fictitious, spaced at a distance 1 upon a n of the previous spacing. That turns out to be a real convenience. So we set d is equal to d dash upon n and write the Bragg's law in the form of lambda is equal to 2d sin. So that is the diagram of Bragg diffraction. Now next one is the X-ray diffraction techniques. Diffraction can occur when the Bragg law is satisfied. This quantity theta and wavelength are very distinguish the three main diffraction methods. First one is the Lau method, rotating crystal method, powder method. So when it is Lau method, wavelength is the variable, angle is fixed. Rotating crystal method, wavelength is fixed, then theta is the variable in part. Then powder method, wavelength is the fixed, theta is the variable. Now starting with the first method, Lau method. The Lau method was the first diffraction method ever used, and it is reproduced von Lau's original experiment. A beam of white radiation is continuous spectrum from an X-ray tube is allowed to fall on a fixed single crystal. The Bragg's angle theta is therefore fixed for every set of planes in the crystal, and each set of peaks out and diffracts that particular wavelength, which satisfies the Bragg law for the particular values of d and theta involved. Each diffracted beams thus has a different wavelength. There are two variations of the law method depending on the relative position of source, crystal and film. In each, the film is flat and placed perpendicular to the incident beam. The film in the transmission law method, the original law method, is placed behind the crystal so as to record the beams diffracted in the forward direction. This method is so called as because the diffracted beams are partially transmitted through the crystal. In the back reflection law method, the film placed between the crystal and the X-ray source, the incident beam passing through a hole in the film, and the beams are diffracted in the backward direction and direction. So following diagram gives the idea of how to perform the law method, transmission and back reflection. Next one is the powder method. The crystal to be examined is reduced to a very fine powder and placed in a beam of monochromatic X-ray. Each particle of the powder is a tiny crystal oriented at random with respect to the incident beam. Just by chance, some of the particles will be correctly oriented so that their 100 planes, for example, can reflect the incident beam. Other particles will be correctly oriented for 110 reflection and so on. The result is that every set of lattice plane will be capable of reflection. The mass of powder is equivalent, in fact, to a single crystal rotated, not about one axis, but about all possible axes. Consider one particle HKL reflection. One or more particles of powder will be by chance be oriented their HKL planes, make the correct Bragg angle for reflection one plane in this set, and the diffracted beam form. If this plane is now rotated about the incident beam as axis in such way that theta is kept constant, then reflected beam will travel over the surface of cone, the axis of cone coinciding with the transmitted beam. This rotation does not actually occur in the powder method, but the presence of large number of crystal particles having all possible orientation is equivalent to this rotation, since among these particles will be a certain fraction whose HKL planes make the right Bragg angle with the incident beam and which at the same time lie in all possible rotational position about the axis of the incident beam. The HKL reflection from a stationary mass of powder thus has the form of a cone of diffracted radiation, and a separate cone is formed for each set differently spaced line. Next one is the Deviation method. A narrow strip of film is curved into a short cylinder with a specimen placed on its axis and the incident beam directed at right angle to this axis. The cones of diffracted radiation intersect the cylindrical strip of film in lines, and when the strip is unrolled and laid out of flat, the resulting pattern has the appearance of the one illustrated in figure. Actual pattern produced by a various metal powders. Each diffraction lines made of a large number of small spots, each from a separate crystal particle. The spot lying so close together that they appear as a continuous line. The lines are generally curved unless they occur exactly at 2 theta is equal to 9, when they will be straight. From the measured position of a given diffraction line on the film, theta can be determined, and knowing x, we can calculate the spacing d of the reflecting lattice planes which produce the line. So following diagram is clear the concept of how to Deviation powder method experimental view. So we'll get the relation of film specimen and incident beam, and second one is the how to that appear of film laid out of flat. Now next one is the conversely, if the shape and size of the unit cell of the crystal are known, we can predict the position of all possible diffraction lines on the film. The line of lowest to theta value is produced by reflection from the plane of the greatest spacing. In the cubic system, for example, D is a maximum when h square, k square, l square is minimum, and the minimum value of the term is 1, corresponding to HKL equal to 100. The 100 reflection is accordingly the one of lowest to theta value. The next reflection will have indices HKL corresponding to the next highest value of S square, K square, L square, namely 2, in which case HKL equals 110 and so on. So this diagram shows the Deviation powder patterns. First one is the copper, that is the FCC, base center cubic. Second one is the tungsten, base center cubic. Third one is the zinc, that is the HCP, that is the filter copper radiation. Camera diameter is the 5.73. Next one is the derivation of Scherer formula for size. Crystal has a thickness T measured in a direction perpendicular to a particular set of reflection plane figures. Let there M is equal to 1 planes in the set. We will regard the Bragg's angle theta as a variable and call the angle which exactly satisfies the Bragg law for the particular values of x and d's and y. In figures raise A and D, lambda is equal to 2b sin theta b. This angle theta b with the reflecting planes. The ray d dash scattered by the first plane below the surface is therefore one wavelength out of phase with A dash, and ray m dash scattered by the m plane below the surface. M is wavelength out of phase with A dash. Therefore, at a diffraction angle 2 theta b, rays A dash and D dash and M dash are completely in phase. You need to form a diffracted beam of maximum intensity. A beam of maximum intensity, since the intensity is proportional to the square of the empty. So, following diagram shows the effect of crystal size on a diffraction. Now, when we consider incident rays that make a Bragg's angle slightly different from theta b, we find the destructive interference is not complete. Ray B, for example, makes a slightly larger angle theta 1 such that ray L from the M plane below the surface is M plus 1, wavelength out of phase with B dash, the ray from the surface plane. This means that midway in the crystal there is a plane scattering a ray which is 1/2, actually in an integer plus 1/2, wavelength out of phase with ray B dash from the surface plane. These rays cancel one another, and so do the other rays are similar pairs of planes throughout the crystal. The net effect being that the rays scattered by the top half of the crystal annual those scattered by the bottom half. The intensity of the beam diffracted at an angle 2 theta 1 is therefore 0. It is also 0 at an angle 2 theta 2, where theta 2 is such that ray n dash from the M plane below the surface is M minus 1. Wavelength out of phase with ray C dash from the surface plane. It follows the diffracted intensity at angle near 2 theta b but not greater than 2 theta 1 or less than 2 theta 2. Is not 0 but has a value intermediate between 0 and the max intensity of the beam diffracted at angle 2 theta b. The curve of diffracted intensity versus 2 theta will this have the form of figure A, the contrast to figure B, which illustrate the hypothetical case of diffraction occurring only at the exact Bragg angle. So that diagram shows the effect of fine particle size of diffraction curves. So it is the 2 theta versus intensity. Next one is the width of diffraction curve in figure increases, the thickness of the crystal decreases. The width B is usually measured in a radians. Intensity equal to half the maximum intensity. As rough measure B, we can take half of the difference between the two extreme angles at which the intensity is 0. B is equal to 1 half 2 theta 1 minus 2 theta 2 is equal to theta 1 minus theta 2. The part difference equation for these two angles are 2t sin theta 1 is equal to m plus 1 lambda, 2t sin theta 2 m minus 1 lambda. By subtraction we find t into bracket sin theta 1 minus sin theta 2 is equal to lambda 2t cos theta 1 plus theta 2 upon 2 sin theta 1 minus theta 2 upon 2 is equal to lambda, but theta 1 and theta 2 are nearly equal to theta p, so that theta 1 and theta 2 is equal to 2 theta p approximately, and sin theta 1 minus theta 2 upon 2 is equal to theta 1 minus theta 2 upon 2. Therefore 2t theta 1 minus theta 2 upon 2 cos theta p is equal to lambda. So t is equal to lambda b cos theta p. So a more exact treatment of the problem is gives t is equal to 0.9 b cos theta b, which known as the Xray formula. It is used to estimate a particle size of very small crystal measured width of their diffraction curves. Next one is the application of XRD or X-ray diffraction. XRD is a non-destructive technique. Some of the uses of X-ray diffraction are differentiate between crystalline and amorphous material, determination of the structure of crystalline materials, determination of electron distribution with the atoms and throughout the cell, determination of the orientation of single crystal, determination of the texture of polygrain materials, measurement of strain and small grain size. So that is the XRD diffractometer setup. So as the X-ray tube, we have to put up the sample powder and we have to generate the X-ray diffraction. Next one is the neutron diffraction. By making a small opening in the wall of the chain reacting pipe, a beam of neutrons can be obtained. The neutron in such a beam have a kinetic energy extending over a considerable range, but a monochromatic beam, that is a beam composed of neutrons with a single energy, can be obtained by diffraction from a single crystal, and this diffracted beam can be used in diffraction experiment. If E is the kinetic energy of the neutrons, then E is equal to 1 half mv square, where m is the mass of the neutron, is 1.67 into 10 raised to minus 24 gram, and v is its velocity. The wavelength of the neutron beam, lambda is equal to h upon square root of 2 me. The neutrons issuing from a pile have their kinetic energy distributed in much the same way as those of gas molecules in thermal equilibrium, that is, they follow the Maxwell distribution law. The largest friction of these so-called thermal neutrons, therefore, has a kinetic energy equal to kT, where K is the Boltzmann constant and T is the absolute temperature. If this fraction is selected by the monochromatic crystal, then we can insert E is equal to kT in equation. Find lambda is equal to h upon square root of 2 mkt. T is the order of 300 to 400 A, which means that X is a 1 to 2A, that is of the same order of magnitude as a X-ray wavelengths. Next one is the diffraction experiment are performed with neutron diffractometer, in which the intensity of the beam diffracted by the specimen is measured with a proportional counter filled with BF3 gas. The main difference between neutron diffraction on the one hand and X-ray electron diffraction on the other lies in the variation of atomic scattering power with atomic number Z and with a scattering angle 2 theta. The scattering power of an atom increases and Z increases and decreasing as a 2 theta increases, both for X-ray and for electrons, although not in exactly the same manner. Neutrons, however, are scattered with the same intensity at all scattering angles and with fine disregard for atomic number. In other words, there is no regular variation between scattering power for neutrons, the atomic number of the scatterer. Elements with almost the same values of Z may have quite different neutron scattering power, and elements with widely separated values of Z may scatter neutrons equally well. Some light elements scatter neutrons more intensively than some heavy elements. The following values illustrate how irregularly the scattering power for neutron varies with atomic number. Example, H is 1 as the 2.0 scattering neutral power. It follows the structure analysis can be carried out with the neutron diffraction that are possible only with the great difficulty with X-ray or electron diffraction. Next one is the electron diffraction. Electron diffraction has also been used in the analysis of crystal structure. The electron, like the neutron, possesses wave properties. Lambda is equal to 2 angstrom, E is equal to sk square k square upon 2 mt is equal to s square upon 2 me lambda square is equal to 40. Electrons are charged particle and interact strongly with all atoms. So electrons with an energy of few electron volt would be completely absorbed by the specimen. In order that an electron beam can penetrate into a specimen, it necessity as a beam of very high energy 50 kilo eV to 1 mega eV, as well as the specimen must be 100 to 1000 nanometer. If low electron energy are used, the penetration depth will be very small, only about 50 angstrom, and the beam will be reflected from the surface. Consequently, electron diffraction is a useful technique for surface structure studies. Electrons are scattered strongly in air, so diffraction experiment must be carried out in a high vacuum. This brings complication and it's expensive as well. So these are your diffraction methods. First one is the X-ray, neutron and electron. Parameters wavelength 1 angstrom and 2 angstrom in electron. Energy 104 eV, 0.08 eV and electron 150 eV. Interaction with electron penetrating, interact with nuclei high penetrating, interact with electron less penetrating. Next one is the compare between X-ray and neutron diffraction method. So atomic scattering power varies smoothly with atomic number. In neutron, atomic scattering power varies erratically with atomic number. Atomic scattering power decreases and the scattering angle increases in X-ray. In neutron, atomic scattering power is constant as the scattering angle changes. in X-ray largely intensity magnetic moments in neutrons scattered by beams. Next one is the thermal analysis is the term applied to a group of methods and techniques in which chemical or physical properties of a substance, a mixture of substance or a reaction mixture are measured as a function of temperature or time, while the substance is subjected to a controlled temperature program. TGA, TTA, DSC are thermal analysis techniques. These techniques are used to analyze the behavior of particular substance when the temperature is changed. These techniques are also applicable in certain chemical reaction in order to find the relationship between reaction and the temperature. The main difference between TGA, TTA and DSC is the method of measuring the changes in samples that are caused by heat. So these are the various thermal analysis techniques, their symbols and which property are measured. So first one is the TGA, that is the Thermo-gravimetric analysis, which measures mass. Second one is the DTA, Differential Thermal Analysis, differential temperature. Next one is the DSC, Differential Scanning Calibrometric, it is the measure enthalpy. Next one is the DTG, it is the derivative of thermogravimetric, first derivative of mass change. Next one is the TMA, that is the thermomechanical analysis, which measures the mechanical property. Next one is the DMA, that is the dynamic mechanical analysis, which measure a viscoelastic. Next one is the TGA, that is the thermogravimetric analysis. Thermogravimetric analysis TGA is an analytical technique used to determine a material thermal stability and its fraction of volatile components by monitoring the weight change that occurs as an specimen is heated. The measurement is normally carried out in air or in an inert atmosphere such as helium or argon, and the weight is recorded as a function of increasing temperature. Sometimes the measurement is performed in a lean oxygen atmosphere 1 to 5% O2 in N2 or helium to slow down oxidation. The technique is useful strictly for transformation involving the absorption or evolution of gases from a specimen consisting of a condensed phase. Measurement of changes in sample mass with temperature are made using Thermo Balance. The balance should be in a suitably enclosed system so that the atmosphere can be controlled. Suitable sample of TG are solids that undergo one of the two general types of reaction. First one is the reactant, which produces product plus gas, a mass loss. Second one is the gas plus reactants, which generates a product, a mass gain. Process occurring without changing mass. Example, the melting of a sample obviously cannot be studied by TG. A plot of mass versus temperature, thermogravimetric curves or TG curves permits evaluation of thermal stability, rate of reaction, reaction process and sample composition. Next one is the block diagram of TGA, thermogrametric instrumentation. So we have used the balance, furnace, temperature program controller and recording. So thermogrametric instrument should include several basic components to provide a flexibility necessary for the production of useful analytical data. First one is the balance, second is the heating device, third one is a unit for temperature measurement or control, a means for automatically recording the mass and temperature change, and last one is the system to control the atmosphere around the sun. Next, so starting with first block is the thermo balance. Balance must be remain precise and accurate continuously under the extreme temperature and atmospheric condition, should deliver a single signal suitable for continuous recording. Null deflection weighing mechanism are favored in TG as they are ensure that the sample remains in the same zone of the furnace irrespective of changing mass. Sensitivity of balance is equal to 1 microgram for a 1 gram maximum load balance. The output weight signal may be differentiated electronically to give a derivative thermogrammetric curve, that is the DTG. So these two diagrams give the thermo balance blocks inside the thermo balance blocks. Next one is the furnace is normally an electrical resistive heater. Some basic requirements of heating chambers are: be inductively wound, be capable of reaching 100 to 200 degrees Celsius above the maximum desired working temperature, have a uniform hot zone of reasonable length, reach the required starting temperature as quickly as possible, not affect the balance mechanism through radiation or convection. In order to overcome the problem of possible temperature gradient, infrared or microwave radiation have been used in some equipment. Infrared heating, some halogen lamp temperature up to 1400 degrees Celsius. Heating rate can be as high as 1000 degrees Celsius per minute. Accuracy is about plus minus 0.5 degrees Celsius. Microwave heating, large sample can be used because uniform heating generated with sample, but temperature measurement and power control are difficult. Heating of the furnace with a constant heating rate beta T0 T is equal to T1 beta T. Temperature of the furnace, then T1 is the starting temperature of the furnace, T is the time, and beta is the heating rate, that is the temperature. So that is the characteristic shows the relation between the temperature of furnace and time. So next one is the thermo balance concept are normally housed in a glass or metal system to allow the operation at pressure ranging from the high vacuum, that is the less than 10 raised to minus 4 Pascal, to high pressure is the greater than 3000 kilopascal of inert and oxidizing, reducing or corrosive gases. Care must be taken to correct for buoyancy arising from the lack of symmetry in the weighing system. Thermal convection is responsible for noise in the signal of TG. The use of dense carrier gases at high pressure in hot zones with large temperature gradients gives the most noise. Fitting of convoluted baffles was found to be more successful in reducing thermal convection. Next one is the temperature measurement and calibration. Platinum resistor thermometer or thermocouples are used for temperature measurement. Large difference between sample temperature Ts and furnace temperature Tf can exist, sometimes as high as 30 degrees Celsius. Calibration is thus needed. The difference or lag is more marked when operating in vacuum or in fast flowing atmosphere and with a high heating rate. So that is the heat radiation from furnace windings and gas flow, and we have to use a thermocouple. Next one is the temperature calibration for a small furnace can be done by making use of the melting point or Curie points of the range of metals and alloy. A series of high purity wires may be suspended in the region where the specimen crucible would normally be located. If the furnace temperature is slowly raised through the melting point of a particular wire, a significant weight loss will be recorded when the wire melts. A series of fusible wires such as indium, lead, zinc, aluminium, silver and gold and their corresponding temperature should have a reasonable calibration curve. So that diagram shows how to calibrate a temperature. Next one is the atmosphere. Salt, pressure, flow rate of the gas in the sample chamber influence the following parameter. First one is the sample reaction with gas, oxidation in the presence of oxygen, heat transition, different heat conductivity of the gas used in an experiment, buoyancy and current effects, different density and flow rate of the gas used in an experiment. For all thermoanalytical investigation, it is very important to report the salt, the pressure and the flow rate of the gases used in the experiment. Then applications are only for the studying thermal events accompanied by mass change, provide valuable information for distortion, decomposition, oxidation, dehydration. Knowing of thermal stability can give information on problems like the hazards of storing explosive, shelf life of drugs, etc. TG curves can also be used for fingerprint purpose. The thermal balance in a TG equipment can also be used to measure vapor pressure of a sample and magnetic susceptibility, and etc. Three factors should be noted when we get a TG curve. First one is the general shape. Next one is the particular temperature at which change in mass occur, severely affected by many experimental conditions. The magnitude of the mass changes much more used directly related to the specific stoichiometry of the reaction, independent of the many factors that affect the shape of the curves, can be used for precise quantitative analysis. Next concept is the differential thermal analysis, that is the DTA. So there is the shows the block diagram and their corresponding characteristics, temperature versus weight. So DTA is a technique in which the difference in temperature between a substance and a reference material is measured as a function of temperature, while the substance and reference material are subjected to a controlled temperature program. In today's market, most manufacturers no longer make a true DTA but rather have incorporated this technology into a thermo-gravimetric analysis TGA, which provide both mass loss and thermal information TGA DTA. With today advancement in software, even these instruments are being replaced are true TGA DS instruments that can provide temperature and heat flow of the sample simultaneously with mass loss. Now, next one is the application of DTA. DTA picks the results from both physical change and chemical reaction induced by the temperature changes in the sample. Physical processes that are endothermic include fusion, vaporization, sublimation, absorption and desorption. Adsorption and crystallization are generally exothermic. Chemical reaction may also be exothermic and endothermic. Endothermic reaction include dehydration, reduction in gases, atmosphere, and decomposition. Exothermic reaction include oxidation in air or oxidation, polymerization, and catalysis. In general, DTA is considered a qualitative technique, although able to measure the temperature at which various changes occur. DTA is unable to measure the energy associated with each event. DTA is a widely used tool for studying and characterization of metal and ceramic material, and etc. Application of DTA. The DTA curve can be used only a fingerprint for identification purpose, but usually the application of this method are the determination of phase diagram, heat change measurement, and decomposition in various atmospheres. DTA is widely used in a pharmaceutical and food industry. DTA may be used in a cement industry, mineralogical research, in a environmental studies. DTA curves may be also used in a dead bone remains or to study a archaeological materials. Next one is the DTA thermogram. So that diagram shows the relation between a temperature and endo and exothermic of material. Differential thermogram DTA showing the types of changing encounter with polymeric material, showing TG, TC, and PM oxidation. Peak areas are A is equal to minus E, G, M, H. So where is the K is the thermal conductivity, G is the calibration constant, M is the mass of it. DTA is also widely used in a ceramics and metal industry. This technique is capable of studying high temperature process up to 2400 degrees Celsius for some units and relatively large sample size, 100 of milligrams. Next one is the DTA thermograph. So that is the construction of an instrument of DTA. typical instrument. So physical and chemical changes in polymetric material that can be studied by different thermometers. Note the thermal transition for a polymer often take place for a extended temperature range because even a pure polymer or a mixture of homologous similar structure, not a single chemical species. So that is the instrumentation of DTA that is required. It is up to 500 degrees, 15 degrees Celsius thermocouples and purge gas. So TC is the thermocouple. Sample size is 1 to 20 mg. Reference is inert materials like as a glass, silicon chloride, etc. Phase diagrams using DTA. So we can measure the phase by using DTA. So differential thermograms, it gives the one example of sulfur. Phase diagrams and a important use of DTA for the generation of the phase diagram and the study of phase transition. For an example shown in figure, which is a differential thermogram of sulfur, in which the peak of 130 degrees Celsius corresponding to the solid phase change from the rhombic to the monoclinic form, the peak of 124 degrees Celsius correspond to the melting point of the element. The sulfur is known to exist in at least 3 forms, and the peak at 179 degrees Celsius apparently involves this transition, whereas the peak at 446 degrees Celsius corresponding to the boiling point of cell. Now compare TJ and DTA. TJ is the thermo-gravimetric analysis. DTA is differential thermal analysis. The change of the mass of sample with the change of the temperature is observed at length. The temperature difference developed between a sample and reference compound is measured. At identical heat treatments used to analyze inorganic materials, metals, polymers, plastics, ceramic, glasses, composite material. Used to analyze thermal properties of minerals for the characterization of polymers and biological materials. The sample can be used in a solid substance in TJ. Samples can be used as a solid substance also. Thank you.